It's a great pleasure to introduce Gabriele Pfister for today, to give today's seminar. Gabby got her PhD in 2000 in meteorology and geophysics from the Karl Franzens University in Graz, Austria. Her graduate research focused on studying atmospheric shortwave radiative transfer using a combined approach of modeling and experimental work. And she started out making measurements, both ground-based and airborne, with broadband radiation sensors and spectroradiometers, and looked at photolysis rates of JNO2 and JO singlet D for her thesis work. She then did a postdoc, one-year postdoc at NIWA in Lauder, New Zealand, and then came to NCAR with 2 consecutive Erwin Schrödinger postdoctoral fellowships to work with the Moppet group here, and then also with the modeling group. And her first work was focused on quantifying the limitations of the Moppet methane retrievals and helping us understand why we really couldn't get those retrievals out of the data. And she then moved to modeling and learned Mozart and did some inverse modeling with Moppet CO in the global Mozart model. She then had an ASP postdoctoral fellowship and was a project scientist, became a scientist 1 in 2007 and a scientist 2 in 2010. And during these years, she's become a lead developer in WRF-Chem and added the Mozart mechanism to WRF-Chem so that we have a fully coupled system of global and regional models. She's been provided a lot of scientific and technical guidance to the user community for WRF-Chem and has been an instructor for the tutorials. She's a mentor for postdocs and visitors using WRF-Chem here at NCAR, and she's been involved with a lot of NCAR activities, such as an ACD representative for the NCAR Industry Summit, organizer of the Junior Faculty Forum, and worked a lot with the media and provided press releases. And without further ado, she will now tell us about tropospheric ozone.
Thank you very much, Luisa. Can everybody hear me? Or perfect. So thanks for the very kind introduction. It makes me feel old hearing that long history. So I'm going to talk about current and future summertime ozone pollution over the US. First of all, why do we care about how much ozone we have in the troposphere when there is actually so much less here in the troposphere compared to the stratosphere? Well, for 3 main reasons. It's a key, it plays a key role in tropospheric chemistry, and I will show that on the next slides. Ozone is a greenhouse gas, which means it has implications for climate, and tropospheric ozone has also adverse effects for human health and the environment. Ozone is not emitted directly. It is a secondary pollutant. It is formed from precursor emissions, which include emissions of volatile organic compounds, NOx, and CO. So once these emissions get into the atmosphere, they react in the presence of sunlight and form ozone. The ozone chemistry in the troposphere is very complex, and I'm really only trying to give you here a very, very simplified version of the ozone production that takes place in the troposphere. So it starts when we oxidize a carbon monoxide or a VOC molecule, and we create peroxy radicals, which then, when they react with NO, create NO2, which then can get photolyzed and with the atomic oxygen lead to the production of ozone. So extremely simplified version just to give you a feeling for how we create ozone in the troposphere. Now this cycle can be interrupted, and 2 things can happen. One, you can form reservoir species. Example is PAN. And these reservoir species have a longer lifetime than NOx, which means they can extend the lifetime of NOx, they can get decomposed again in NOx and lead to ozone production somewhere far downwind of a source. Or this cycle can be interrupted by creating termination species such as nitric acid, which is very soluble and is washed out from the atmosphere. Ozone, as well as its precursors, are then also transported and mixed in the atmosphere. And another factor that impacts how much ozone we have in the troposphere is the stratosphere-troposphere exchange. And then The ozone that we find in the troposphere, we label it often as the bad ozone because of its impact on human health and the environment. Actually, decades ago, it was considered that the more ozone you breathe, the healthier it is, because after all, it's O3, so it must be really, really good for you. But now we know more about it, and we know that it has adverse health effects ranging from respiratory issues all the way to cardiovascular issues, and it is also assumed that it causes premature mortality. There is, for example, I just show here a study by Silva et al., and they estimate that the current premature mortality because of anthropogenic ozone pollution can be in the order of about 500,000 people per year. So it is a huge impact on human health. Exposure of high ozone also causes damage to plants and reduces crop yields. So here you're seeing a picture from the ozone garden at the St. Louis University, and I'm showing here a sensitive to ozone plant, a soybean cultivar that's sensitive to ozone, and you see the damage when it's exposed to high ozone. The estimates due to reduced crop yields are in the order of about a few billions of dollars worldwide. So it is a huge economic loss. Now, in the US, over the last decades, we have implemented emission controls, but despite these emission controls, high surface ozone remains still a concern in the US, and not only in the US, it's a concern worldwide. What I'm showing here is an analysis of surface observations at EPA monitoring sites. I'm showing here the time period 95 to 2000, and here 2005 to 2010. And what is shown in the colors is the percentage of days during summertime when the ozone health standards, we call that the NECs, was exceeded. And you see that even nowadays, there are large areas in the US that are violating the health standards. And this is actually to be expected to be even worse because the current standard is at 75 ppb. And EPA is considering to lower this standard to something in the range of 65, which then is also much more in line with what you expect from health studies and what also is at the moment implemented in Canada or Europe. Based on a 2012 estimate by the EPA, there are about 140 million people in the US living in counties that violate the health standards for one or more pollutants. And nearly the same number is estimated to live in counties that violate the health standards for ozone. So clearly, ozone pollution is still a big issue in the US. And the question is, do we understand it? Well, what I'm showing you here is a model in the comparison that we conducted as part of the NASA ACAS team. So our results from WRF-Chem and from Mozart are shown here, and compared to some other regional and global models. The graphs show you surface ozone for summer 2008. And what you see first is that all the models show quite some large differences. And what you also see is, if you compare this to observations, well, also all the models show large differences to the observations. So clearly, there are some processes that we do not yet fully understand. And these processes are related to the chemistry, to the emissions, as well as the transport of ozone. The chemistry of ozone is a very complex response to levels of VOCs and NOx in the atmosphere, and also a very complex response to the state of the atmosphere. This includes how much radiation is available, as well as meteorological parameters such as temperature, relative humidity, and winds. The ozone chemistry is nonlinear, which means that it has a nonlinear dependence on VOC and NOx concentrations. VOC here in NOx. So for example, if we were to reduce NOx by 50%, this doesn't mean that tropospheric ozone is being reduced by 50%. It can get reduced by more, by less, or it can even increase. And so this makes it very challenging for developing emission control scenarios. We do understand the fundamentals of the ozone chemical cycle very well. But there are still a lot of gaps that we need to fill in regard to our understanding. And I really only want to bring a few of the research challenges here, such as, for example, the fate of NOx or the role of halogen chemistry or heterogeneous reactions on tropospheric ozone, or the chemistry that's going on in very fresh plumes, specifically in fire plumes. There are many unknowns in this regard. Transport is a big factor in moving and mixing pollutants, and so ozone and its precursors around. And we really need to be able to characterize the transport on all different spatial and temporal scales. And this ranges from very localized flow patterns to intercontinental pollution transport and stratospheric tropospheric exchange. So we need to be able to handle all these different scales. And last but not least, emissions. Precursor emission sources range from anthropogenic sources, fires, biogenic sources, to ozone production from lightning NOx. And all these source terms have a large uncertainty associated with them. This here, just as an example, I show you for Colorado, summer 2012. I'm sure you remember all the extreme fire season we had. These are fire NOx emission estimates from two different inventories. And what you see is first that these different inventories not only have a large difference in regard to their magnitudes, they also show a different timing. So clearly, if we have uncertainties of that magnitude in the emissions, we will have also large uncertainties in the resulting ozone. I want to now go a little bit more into fires and talk about the ozone production from fires. Because if we look in the literature, then we find that studies actually show very, very conflicting results. They show conflicting results if ozone is produced in a fire plume, and if it shows that it's produced, then how much ozone is produced. And why this is because fires are a highly variable source. There is not one fire is the same as any other. How much you emit from a fire depends what are you burning, how efficient are you burning it, in what way are you burning it, what is the fire dynamics, how get the emissions injected into the atmosphere. It depends on where does the plume get transported to, how old is the plume, do we look at the fresh plume or a very aged plume, and has a fire plume been mixing with plumes from other sources. And all these factors vary a lot, and that's why it's just very hard to characterize how much fire, how much ozone is due to a fire. I want to talk about 3 case studies that I've been working on of very, very intense fire seasons. The one are the Alaska fires that happened in summer 2004 during the NASA Intex-A campaign. The other case studies are wildfires in California that happened very late in the season in September, October 2007. And the third case are wildfires in California during one of the most intense fire seasons in summer 2008 during the NASA Arctic Sky campaign. The research objectives of these different studies were to constrain the fire emissions using carbon monoxide that's retrieved from the satellite instrument MOPIT, using the global chemical transport model Mozart-4 and data assimilation. I used these case studies to assess the ozone production using regional and global models, field campaign data, as well as surface monitoring. And I also try to quantify what was the impact of these fires on surface air quality. Let me get started with emissions. So this is work that we did on the case of the Alaska 2004 fires. And what we did is we constrained the emissions of carbon monoxide. So now you're probably kind of, okay, she's looking at ozone and she's doing the emissions for carbon monoxide. Well, there is a reason behind. The reason behind is that carbon monoxide has a very simple chemistry, which makes it a very good tracer for emissions and transport. Plus, for carbon monoxide, we have satellite observations available, which we really don't have for any of the VOCs. But CO is co-emitted with NOx and VOCs from the fires. So by constraining the CO emissions, we can use this information and also basically translate this information to other emission species. So we used a rather new approach to inverse modeling in this study, in that we applied data assimilation of Moped CO outside of the fire region in the Mozart-4 model. And this actually helped us to constrain the transported or the background CO in the model, which means we were able to reduce the model error. And then we applied an inverse modeling method over the source region of the Alaska fires and constrained the CO fire emissions. The results I'm showing here, this is a time series of the fire emissions. In blue is the a priori, and in green are our posteriori emissions. And what you see is that we had to increase the emissions by about a factor of 2 in order to achieve a better agreement with the Moped data. And we also had to apply some change in the temporal variability. The study then also, we did an evaluation with independent data from aircraft as well as some ground sites, and we definitely achieved a much better agreement using the posteriori emissions. So now, using this improved emission inventory, we then went on to assess the ozone production from the fires. Now, ozone is very complex, and you can basically have 2 different methods on how you look at the source contribution. The one method is what we call a perturbation method, which means you are modifying the source. So in our case, what we did was we conducted a simulation without the fires, and then by looking at the difference in the ozone that's simulated without fires and with fires, we can say how much ozone is due to the fires. Another method that we are using in the global Mozart-4 and Chem models, as well as in the WRF-Chem model, is to apply synthetic model fire tracers. Our synthetic model tracers are basically, these are tracers, different colors of a molecule, as if you want to see it that way. And they basically act in parallel to the standard mechanism. So they basically undergo the same chemistry, the same loss processes as any of the standard species, but they do not impact the standard species in turn. And we are using a tracer for CO, which is actually because CO has a rather simple chemistry. So we do this by tagging CO fire emissions, the direct emissions, and then also follow the loss through oxidation, and we also have it deposited, for example. Ozone is more complex. In this case, we are tagging the NOx fire emissions, and then we have to add a lot more tracers into the model because we are following the tagged nitrogen then through all the nitrogen species, so all the reservoir species, all the termination species, all those species to the production of ozone. So these two methods we used in the case of the Alaska fires, and what I'm showing you here is the difference in the tropospheric ozone column between the simulation with fires and without fires. So I show you the result for the perturbation method. And what you see is there is quite a significant impact, quite a significant increase in tropospheric ozone because of these fires, and that this was a very, very widespread impact with basically reaching all the way over to Europe. So right in the pathway of this pollution plume, there is actually are the Azores, and on top of the Pico Mountain there, Michigan Tech runs a measurement station, and that's the Piconare station. And so in a study, we collaborated with Michigan Tech to look how these fires impacted this measurement site. And so what I'm showing you here is a time series at Piconare of the estimated ozone that is due to these Alaska fires. And I show you the fire tracer as a solid line, and I show you the result from the perturbation method, so the difference with fires minus without fires in the dashed line. And what you see is, well, okay, both estimate that there was a significant impact, both give you a very similar temporal variability, but they are quite a bit different in the magnitude. So which one's right? Well, there's not really one right or wrong, they are just different, because ozone is such a complex species, it has such a complex and nonlinear chemistry. When we do the tagging, it gives us a budget term. It gives us a contribution term. Because our tracers, they don't change the chemical regime. So the chemical regime with the fires, it stays the same. While if we are using a perturbation method, by turning off the fires, we basically change the atmospheric composition. And this changes the chemical regime, which then impacts the ozone production in loss terms. Another difference is that in the tagging method, the way we apply it is we're only tagging NOx. So we are not tagging VOCs. So this means if we have, for example, a fire VOC that comes into an urban area and reacts with an urban NOx, this is no longer a fire ozone. While in the case of the perturbation method, we shut off all the fire emissions, NOx, VOCs, particles, absolutely everything. So I just want to also show this because it really demonstrates how tricky it is to do a source estimate for ozone simply because of this nonlinearity in the chemistry. Plus, for the perturbation method, you could do a lot of different tests. You could reduce your emissions by 20%, or you could just turn off one type of emission. So whenever you are looking at ozone contributions, it's really, really important to look at what approach was used and what were the assumptions made. So one thing that we saw in the Alaska fires was that there was a really widespread impact. Remember, we saw impact all the way over to Europe. And what we actually found at Piconare was that there was still significant ozone production going on at that site. Now, the question is, how do you get, if the NOx lifetime is at the most a week in the free troposphere, how do you get that ozone production that far downwind? And the hypothesis is that pan plays an important role in this regard. So pan, a reservoir species, is produced from the fires, and it is very stable at low temperatures, such as you find at the higher altitudes. So at high altitudes, it can get transported over very far distances. And then when it subsides, it decomposes and it can release NOx that then can lead to the ozone production. And in order to test how important this pathway is for redistributing fire emissions, we did a study based on the California summer 2008 wildfires. And in this case, we used the WRF-Chem model with the ozone fire tracer. And I show you here results for one specific day. You see that we have, so here is the WRF-Chem surface ozone with EPA monitoring site results overlaid. So the observations are the dots. And you see there's very high ozone in Northern California. And this is due to the fires, because most of the fires during this time period were actually in Northern California. If you look at the ozone fire tracer, then we see that, yes, a large part of this high ozone that we observed here is indeed estimated to be due to the fires. So now we ran also one sensitivity simulation, and in this simulation, we changed the chemical mechanism, and we did not allow ozone to be produced from pan recycling from the fires. So this way, we can estimate how much of the fire ozone is due to pan recycling, pan decomposition. And we find that in this case, nearly about half of the fire that is half of the ozone that is due to the fires was produced through the pan cycle. So this confirms that pan decomposition is really an important part in redistributing fire emissions and causing regional ozone enhancements that can happen very far downwind of the source. We also found significant ozone or clear ozone enhancement when we looked just at the data. So what I'm showing here is aircraft profiles of ozone from the NASA Arctic Scarp campaign. We had 4 flights over California during the time period. And I use actually the measured acetonitrile concentrations to separate the data set into measurements that were impacted by fires and measurements that had very little impact or no impact from fires. Acetonitrile is mostly just emitted from fires, so it can be used as a very good data filter for this purpose. And what you see first is, if you look when there was no fire, then we see that the model does a very nice job actually in getting the aircraft data right. And then if we look at the fire impacted data, first of all, we see, yes, both model and observations get higher ozone concentrations. But what we also see is we have much, much higher uncertainty in the models. And this basically reflects the challenges that we modelers face in simulating such a highly variable source as wildfires. And we see pretty much a similar picture if you look at PAN. We find generally higher PAN when the data were impacted by fire plumes, and we also find much larger model uncertainties. We also looked at so we saw that ozone is impacted by fires in the troposphere. We also looked more closely into quantifying this impact on surface air quality, and we did this on the California 2007 fires. In this case, what we did was we did a statistical analysis using surface ozone observations from the EPA monitoring network and the global Mozart-4 model. And we looked at the change in the observed and the modeled surface ozone as a function of the degree of fire impact, and we used our fire tracer for this purpose. And what we found was that we found a clear enhancement when there was a significant fire impact in both the observations and the model that was in the order of about 10 ppb. And in regard to the health standards, we found that the violations of the NECs were estimated to be about 3 times more likely because of pollution from the fires. So it is a significant factor when you're looking at not only the tropospheric composition, but also at surface air quality. I want to change slightly topic, but I want to stay with my focus on California and want to look at another process that can have a significant impact on ozone levels in California, and this is intercontinental pollution transport. Studies suggest that specifically in the Western U.S., pollution inflow can be an important contribution, and studies also show that over the recent years, it looks like there has been an increase in the U.S. background ozone or the transported ozone. If we want to look at intercontinental pollution transport and we want to look at local pollution, then we have to cover these two very wide ranges also in our modeling systems. And we do this by integrating the global Mozart-4 model with the WRF-Chem model. Louisa mentioned already, we use for both of them the same chemical mechanism and as much as possible the same physics schemes. And the way we use the models together is by having Mozart-4 providing the chemical boundary conditions for our WRF-Chem domain. And we are actually on our website, we are making model output from the global model as well as tools in order to use the global model output for WRF-Chem. We make those tools available, and there is actually a huge demand in the community. So I think based on our latest user statistics, since September last year, we had over 500 downloads. So this is really something that's very welcome by the community. Now, with having satellite data available and models, we realized that the intercontinental pollution transport is a highly variable feature in our atmosphere. But really, until recently, air quality models employed constant boundary conditions. It was kind of 40 ppb at the boundaries, and that stays the same with time, with space, whatever else, and that's how we do it. But the question is, well, is this really adequate, or what is the consequence if you are not considering this variability? In order to study this, what I did was I ran 2 different WRF-Chem simulations. In one simulation, I used time-varying boundary conditions. In the other one, I averaged my boundary conditions over the 2-week time period of my WRF-Chem simulation, and then it looked at how do the regional model simulations differ. And I'm showing this here. What I'm showing here are maps, daily maps of the difference in surface ozone between these 2 simulations. And if you look at the scale, there's actually a really large difference. So the differences are in the order of plus minus 15 ppb, which is quite significant. And also, by not considering the variability, we are smoothing out any of the structures that we would have in the boundary conditions, which means we are reducing the frequency of the high ozone events. So for example, if we look at the exceedance of the 8-hour ozone standard, we find that if we have time-varying boundary conditions, we get a frequency of about 10%. Well, if we use the time-average boundary conditions, we only get about 8%. And for a lower health standard, for 65, this difference is even more pronounced. We have 25 versus about 18%. So boundary conditions clearly matter.
Can I ask a question about that?
Yes?
From the movie, there was clear sort of pulses of ozone coming from the east coast of the U.S.
Yeah.
And when you fix the boundary conditions, those went away.
Because I'm just averaging out them. Then basically, you know, you have, it depends on the transport when you have basically the plumes going out, but over a 2-week time period, you're just...
But those plumes clearly have a local component because they're not ejecting across the whole U.S., right? They're appearing in situ over the...
Yeah, these ones.
Yeah.
No, these are basically a lot from pollution that is produced over the East Coast, and that gets lofted and that gets then transported.
So that change in pollution emissions is not in the right-hand movie?
No. Well, no, it is, but the thing is you wouldn't see the pulses because I'm averaging over 2 weeks. You still see that overall you have higher ozone in this region, but you are of course not seeing this temporal variability.
Okay, so this is not a regional model simulation.
No, this is the global model that gives you the boundary conditions.
Okay.
Sorry, I did not make that clear. I apologize for that. So this is the Mozart 4 simulation that provides me the boundary conditions. And that's then makes sense. Okay. Sorry, I should have put it up there. So now basically what we are doing is we want to look at what is the contribution of this pollution inflow. And for this purpose, we are setting up a 2-domain WRF-Chem simulation. And we are tagging ozone and the ozone precursors at the lateral boundary conditions of the outer domain. So we are taking basically the ozone and the ozone precursors from the Mozart 4 model, and we are tagging that, and then we follow our tracer through the model domain. To show you an example how that looks, these are ozone sound profiles at Trinidad Head during summer 2008. Trinidad Head is located on the west coast in California. I show here in black, you see the observations, and in red, you see the model results. And so we are doing a fairly good job with the model in getting the average profile shape and the variability at Trinidad Head, right? And in orange or yellow, however the color comes out, is you see the contribution from inflow. And you see that, as you would expect for a location that's right on the coast here, we do have a significant fraction of the total ozone is due to pollution inflow. And these data here, I, for example, did not filter for wind's direction. If I were to look only at profiles that come really only out from the ocean, then pretty much most of the ozone at Trinidad Head, also at lower altitudes, would be from pollution inflow. Looking at how does this look on average over the US. So this is shows average results for 19th of June to 10th of July. If you look at total surface afternoon ozone, we see in California we have the highest ozone we find in the LA basin and also in the Central Valley. For this time period, we also see it in Northern California. Remember, this is where we had the big fires, so we have also quite some contribution there. If you look at ozone that is attributed to long-range pollution transport, then we see on average, it explains about 10 ppb of the 58 ppb over California. But what we also see is that overall, in those areas where we find the highest surface ozone, we have a rather small contribution. So overall, this would indicate that it's really domestic emission controls that we need to install in order to address the high ozone problems. Now, in very certain cases, long-range pollution transport can indeed be a much more important contribution to high ozone exceedances. And to look at this, what I'm showing you here is the percentage contribution of the incoming ozone as a function of the daily 8-hour maximum ozone over California. And if we look basically at the exceedances of the 75 ppb standard, we see that the average contribution of inflow is in the order of 4%, so it's rather small. But if you look at the 99th percentile, then the contribution can increase up to 15%. And if you look at the 65 ppb, then it can be nearly 1/4 of the total ozone. So while really on average, it is the domestic pollution that basically causes us the ozone problems, there are certain cases where the inflow can indeed be an important contribution. Now, we've seen that ozone pollution in the US is still a problem. And we also have seen that all the factors that are impacting surface ozone or the tropospheric ozone in general, emissions, chemistry, as well as transport, all these are expected to change in a future climate and with a future economy. And so it is really important that we assess how these changes in future climate and future emissions might impact the attainment of air quality objectives. Now, in the past, most air quality climate projections have been using rather coarse model resolutions. While really in order to meet societal needs, we need to look into projections. We need to provide projections at a very high spatial resolution. And also they need to cover multiple years because we need to derive robust statistics and basically consider the interannual variability. And this led us to the development of the nested regional climate model with chemistry. This is work that we did as part of an NSF ESM grant where Greg Holland at M³ is the PI and an accelerated scientific discovery proposal that was led by myself. We conducted a set of simulations with NRCM-Chem to look at future changes in weather and air quality over the US, to assess how changing emissions and changing climate are changing the future tropospheric composition and surface pollution, to look at feedbacks between chemistry and climate, how our projections depend on model resolution or different physics schemes that you're using, and also to test the sensitivity to initial conditions. Our NRCM-Chem is based on the WRF-Chem model, but we added various features to it in order to make it work for a climate model. We performed 3 sets of simulations. Each simulation covers 13 summers, so we have really multiple years to provide statistics for. One simulation uses a present climate and uses the present time emission, so we try to get basically what we have now. Another simulation projects into the 2050 time period using a 2050 climate and 2050 emissions following the RCP 8.5 scenario. RCP 8.5 is a rather aggressive climate scenario with about 8.5 watts per square meter radiative forcing by 2100, but at the same time, RCP 8.5 employs stringent emission controls of precursor emissions for like NOx, CO, and VOCs in the developed world. Our simulations, we conduct them at 12-kilometer grid resolution, and whoever ran a regional model at 12 kilometers over the US for multiple years know where we had an accelerated scientific discovery proposal. Our chemical initial and boundary condition come from Jean-François' Chem simulation, employing the same climate and emission scenario, and our meteorological initial and boundary conditions come from the M³ and RCM model. Let me move on to some results. So what I'm showing you here are surface ozone for, actually I'm showing you the daily 8-hour maximum on average for present time, summertime, and the 2050 future climate and future emission scenario. And what you see is that if we employ future emissions, we significantly reduce ozone levels over the US. We reduce the mean from about 53 ppb down to 41 ppb. And we see that also here in the difference plot, a significant reduction of ozone over the contiguous US. Here over the Pacific, what we find is that actually our ozone is increasing. And this is due to mostly because in the future scenario, we have increased methane levels, which are considered by the boundary conditions, which also increases our global ozone. So the global ozone background is increased, as well as the ozone inflow through the boundaries. So what we see here, we see that domestic emission controls definitely dominate, and here we have basically the increase from the climate impact, mostly in this case of methane. Now, if we were not to apply any emission controls in the US, then this is our scenario. Then we see that also over the US, we find quite a clear increase in surface ozone levels. And yes?
So what did you just go about Asia?
There is a slight increase in the emissions in Asia, and it's a small increase. If you look just in the global model over ozone over Asia, we see a slight increase, but it's much smaller than the increase that is due to methane. It is accounted for. It is accounted for, but it's a smaller contribution. So most of the impact that you see at the boundaries is really from the enhanced global background. And so basically, so if we are not applying any stringent emission controls over the US, then the future climate change, which means increased methane levels, will make our air pollution worse. And if we look at climate variables, we also find we will have, I mean, we all know, increased temperature, which favors ozone production. Increased temperature also leads to increased biogenic emissions, which means we have a lot more biogenic VOC precursors over the US. And our analysis shows also that we will have, or we project for the future scenario, reduced cloudiness and more frequent stagnation events. So all of those favoring high ozone events. We also did a comparison between the regional and the global projections, and I'm showing that here, NRCM-Chem and Chem-Chem, mean daytime surface ozone. And what we see is if you look at the present time scenario, that Chem-Chem has significantly higher ozone. And this is actually explained by the coarse model resolution. So when you are in a model, when you are diluting the precursor emissions, you actually move more frequently into a higher ozone production efficiency regime. And so this is a common feature that we see in global models. And I'm not showing here an evaluation, but if you compare statistically our model, the WRF-Chem model, to surface observations, we actually do get a very good agreement. So by Chem-Chem, the global model looks biased high, but the really interesting and important feature is if we look at the future projection of the change in surface ozone, then we see that both models actually agree very well, which basically lets us suggest that despite the coarse model resolution and despite having maybe a bias, obviously, the global model is also able to resolve all the processes that basically impact the future changes. I would like to come now to a summary and just bring some of the main conclusions. I hope I was able to show you that tropospheric ozone is really impacted by a variety of sources and processes, and that we have to, have a comprehensive understanding of all of them in order to understand ozone. And the two of the important factors in the specifically Western US are wildfires and long-range pollution transport. Regional modeling requires a very careful evaluation and also improvement of chemical boundary conditions, and we definitely have some more work to do in order to improve those and also represent their variability. In order to understand and make future projections of ozone, we need to integrate models and observations on all different spatial and temporal scales. Our studies of present time data and modeling, as well as future projections, have shown that it's really domestic pollution controls that we need to tackle on if we want to address our high ozone issue, and also especially if we want to counteract any possible ozone increases due to changes in climate. We have seen that global and regional model predictions, even they differ in predicting absolute ozone amounts, they agreed very, very well in projecting future changes. And I hope it becomes also clear that with our research, we can really make a very, very important and essential contribution to air quality management and policy making. And I'm not letting you go yet, because I want to also talk just a few more minutes about where do I see this field heading, and where do I actually want to move ahead? We have seen that we do understand a lot about ozone, but there is a lot that we do not understand, and a key to really learning much more and filling the gaps in our understanding of the different processes is to have a very comprehensive, targeted observations to look at the different processes and improve our understanding and our model predictions. And one important step towards this improved understanding we will take with the upcoming Troposphere field campaign that Frank, Flocky, and myself are PIs of. Troposphere will take place in the Front Range, so just here, this summer, jointly together with NASA Discover AQ. And our overall objective is to characterize all the different factors, chemistry, transport, and emissions that are impacting summertime ozone in the Front Range. And we will have 3 aircraft, a bunch of ground-based sites. We have mobile vans, tethered balloons, we have ozone sondes, lots of modeling going on, a huge collaboration, and it's a really, really exciting campaign. And I think it will really bring us a very important step towards understanding our processes better. We also really should work towards developing tools that help us to better analyze and utilize observations. And data assimilation is one very powerful tool in this regard. And our ACRES group is actually actively working on developing data simulation schemes for WRF-Chem and ChemChem, and our 2 experts are sitting here in the audience. And data simulation can help us to improve initial and boundary conditions, help us for inverse modeling studies, and to really provide much more comprehensive analyses of data sets. And in the same token, we also have to work towards linking the different scales in our modeling systems. We should go away from having a global model and a regional model, and we use them separately and still use them together to a seamless prediction. And I see that it's really, really important to make sure that we are working on adding the chemistry component to the MPAS system. And last, but certainly not least, Walter R. Roberts, in his words, we have a very important moral responsibility to apply that research to benefiting humanity. And I see that as I see it actually as a really important responsibility and obligation that we have. And I'm really glad that I have already started bridging the link to the societal sciences. And at the moment, these are 2 of the projects I'm working on together with colleagues at UC Berkeley, Emory University, and the Colorado Department of Public Health and Environment. We were trying to assess what are really the health impacts of wildfires. In the one case, we focused on California, and in the other case, on Colorado. And I think it's really important to build up upon these connections and relationships and take our step and bring our research a little bit further to the applied sciences. And with this, I would like to thank you for your attention, for being here despite a beautiful summer day outside. And I would like to also definitely acknowledge all my colleagues within NCAR, outside of NCAR. I mean, there are too many to name who all basically make your work happen. Thank you. Yes, he.
I was very interested
was very interested by what you said when you compared essentially the global prediction of ozone over the US and the regional, and you saw large differences, in fact, pretty large differences in the two runs, especially in the western part of the US. So in the first case, you were around 50, 60 kilometer resolution, I guess. The second case, you were at 12 kilometer resolution. And so...
right, well, no, this
no, the one before, the picture before.
Yeah.
This
so
one.
Chem was actually run at about 2 degrees, something like that.
Okay. But nevertheless, the difference is large, especially in the western part of the US. And so maybe you could tell us a bit why that is. When you increase the resolution, ozone changes so much. And number two, this is a bit scary because you see most of the models running at high resolution when they do, all these IPCC simulation, etc. So the high resolution seems to be important for the future. And so you mentioned MyPass as a way to go, and I think I fully agree with that. The question that I have is Chem at 15 kilometers at sufficiently high resolution? Or if you went to 5 kilometers, do you think your ozone would double again or increase again?
Yeah, that's a very, very good question. So first of all, what happens is, specifically in areas where you have high NOx, with of course, so if you have, let's say, a 12 kilometer, have a very high NOx emission, but when you're at very high NOx, your ozone production might not be as efficient then, because this is the nonlinearity, and I could go back to that plot, the ECMA diagram that we had there. So you are basically moving into an area, so with the coarse resolution, you're diluting your NOx, you're moving into an area where you have a more efficient ozone production. And that explains a lot of this higher bias here. In regards to, if I would, let's say, if I run with this 12, from this 12 kilometer, if we go down to 4 kilometer, what happens then? I've done that, for example. I've done it not for this huge domain, I've done it for smaller domains. And in general, actually, it depends. The differences are much less pronounced, of course, when you compare 2 degrees or in 12 kilometers to 12 and 4 kilometers. And between 12 and 4 kilometers, I sometimes actually see that also my ozone might be going down if I have then more titration. It depends also what is your model domain. But in general, the differences are smaller. Now, the other for what you mentioned for the IPCC scenarios, well, the important, even we see there is a high bias, I see it as the very important is that the overall processes that lead to a change, and this is really what we are much more interested in. I don't think that we should be concerned. It depends, but it is important. I think we need both. The thing is, we need the high resolution ones to look really, we want to know what's happening in the front range. Well, I don't want to know what's happening over entire Colorado with 5 grid boxes, for example. But I cannot afford, for example, with the current computing resources, you cannot afford run every single IPCC scenario at the 12 kilometer resolution. We already were struggling with getting those simulations done, and we are still struggling with the 200 terabytes of outputs that we are analyzing. But by basically having tests like that show you that, well, the predicted change in the global model is actually going in the right direction, you can then use the global model and conduct sensitivity simulations, for example, for all the different scenarios, and use these together to predict what's happening. Yes, I fully agree with that. Yes, yes.
I have a comment which maybe relates to the resolution business. I noticed that in some of your simulations, particularly the ones about the fire sources, that there's a very strong signal of what I call baroclitic instability and frontal kind of activity. It was all over the place. And particularly in the one with the 2004 Alaska simulation, you could see almost perhaps a tropopause intrusion kind of thing. Does that make any sense that you can possibly in some meteorological situations, get away with rather coarser resolution that one would expect because of this business about synoptic scale dominating?
I agree. And I think this is also the point that we saw in the IPCC simulations, that if you look at the different factors, and I'm not sure where.
That's the one.
That's, for example, the IPCC simulations where we saw that, well, it is definitely large-scale transport features that impact your ozone. It is, in regard to the changes, the methane has a huge impact, and the future temperature changes. And all these can be resolved by a global model. So I say, yes, there are a number of applications where it is totally justified and applicable to use a global coarse resolution model. But then there are other, applications. If you want to know what is the health impact of future ozone projections, well, it is hard to do that maybe with a global model because you are just not getting the tail of the distributions right that is of concern for applications like that.